should you act like you guys do that?
Like 31, 20, 31, 30,
Yeah.
31,
Yeah.
20.
Probably be in all the same classes.
I know.
All right. Well, it is day number 2 of electric circuits for the summer. This means it's July 1st, which means that it can actually be kind of warm today. Finally, summer has finally made its way to the Keweenaw, I guess. So it took long enough. But that might mean that we won't be skiing until like February. I don't know. We'll see. Plan for today is to just kind of plug through. We got some good stuff with reviewing the basic circuit quantities that we looked at yesterday. Look at the last couple of things that were new circuit things that we'll introduce in terms of the voltage and current sources. And then I think we should be able to easily get into starting to look at some resistive circuits. So just on the order of a couple of announcements, one thing is that if you have Firefox 3, either on your personal computer or one of the lab computers, I don't know how quickly they've been updating that, but it is not compatible with MediaSite at the moment. They're working on some fixes, but who knows when those will actually be available. So stick with something like Internet Explorer, Firefox 2, or Safari, something like that, and you should be okay. Second thing is, yesterday I told you not to quote me on the potential Mac incompatibilities with the MediaSite stuff. That works fine with Macintoshes, but you're still kind of stuck if you want to use Linux or Unix or something like that. So if there is somebody has a problem accessing the online course content and you really want to, please let me know. And then the third thing is, just as a reminder, a number of you got it out of the way, but I didn't get anything from any of the online students. Do that quiz 0, stop by and say hi, send me an email that says this is me, this is why I picked Michigan Tech or whatever else. So yeah, I think that's it for announcements. So let's take a look at some of the stuff that we talked about on yesterday. So taking a look at the PowerPoint, we talked about electric current. Electric current is measured in amperes, or just amps. Usually we talk about it. And it was almost always assigned to the variable I. The unit abbreviation is a capital A. It is the movement of charge over time, and there are some questions in the back of the textbook that give you graphs of and functions of here's charge over time, and they ask you to find out what is the current, or here's the current, what is the charge. And it's really, I mean, it's just determining what the function is, and then these piecewise functions, and then applying a derivative or applying an integral. And I'm pretty sure that you guys can do that, so I never ever assign those questions. Anyways, it is a derivative. It is the flow of current over time. Electric charge is the kind of the base unit, but it is defined as the integral of the current. It is an ampere second. We don't talk about charge a ton in this particular class, at least until we get to, we talk about it a little bit more when we get to capacitors, because there's a fundamental relationship with capacitors and charge. But that is what flows around the circuit itself. So we talked about current flow. It's important to indicate that current has both flow, or it has a magnitude and it has a direction, and both of those need to be indicated on your circuit diagrams. We have alternating current and we have direct current. Most of the stuff that we're going to talk about for the first few weeks are direct current. And it's important to remember that what that means is that it's still a function over time. And whenever we write out these things with saying, okay, there's the V of t equals 6 volts, or the I of t equals 6 amps, or whatever, it is a constant function. It just means that at any point in time, if you were to graph it out, it would be a flat horizontal line. But we'll look at alternating current later. What's interesting, or what's useful, is that all of the analysis things that we do, aside from the first and second order transient circuits, you can apply all of those things to alternating current as well. Voltage is the electromotive force. It is a difference in potential between 2 points, just like the difference in potential energy between lifting something above your head and having it at your waist. Measured in volts, assigned to a variable called V, and it is a joule per coulomb, so it's a kind of a funny quantity, to be honest. And just like we have to indicate the direction and the magnitude of the current, we have to indicate the magnitude of the voltage as well as the polarity of the voltage, indicating which of the 2 points has the higher potential. And usually we just put a plus sign for the higher potential, negative sign for the lower potential area. We define something, these voltage current relationships, and this leads into the passive sign convention, that if you have current entering the terminal, the positive terminal of an element, it's going to be receiving energy. If it's entering the negative terminal, then that device is going to be supplying energy to it. And we formalize that even more so after we talk about power in the passive sign convention. So power is measured in watts. Formally, it's just voltage times current, and so a watt is really a volt amp, at least in one way of looking at it. It's work done over a period of time, so there is a time component to our power as well. So the passive sign convention, as we defined it yesterday, and it's very important to keep track of this one, is that you have a voltage V of t, voltage over time, that if it's defined with the current entering the positive terminal, then you can do a simple multiplication of the magnitude and the sign of the current and the voltage, and whatever you get, it tells you the power as well as whether it's receiving or supplying that power to the circuit. So if you get a positive power, that means that the device is absorbing power, and that is traditionally true of it's almost always true of resistors. I think it's safe to say it's always true of resistors. And for the most part, your suppliers are going to be your voltage and current sources. It does get to certain cases when capacitors and inductors can be supplying energy to the circuit, but it only happens under certain circumstances. So, but we did a couple of examples with the passive sign convention, and so this is where we kind of got to yesterday. So we can use the passive sign convention, we can use the relationships that we know already to do a certain amount of analysis of a circuit. So we can take a look at the overhead camera and do a quick, these are very trivial, but it gives you an idea of the kinds of stuff that we'll start taking a look at. We have some sort of device hanging off the circuit. Again, doesn't matter a ton what it is. We have 2 points, A and B. We don't know offhand which one has the higher potential, but we're going to kind of figure that out as we go. We do know that with a watt meter that we are consuming, there's 20 watts, negative 20 watts in that device. And we also know that there happens to be a current flowing through there of 5 amps. So if we know that the current flowing into this device is a positive 5 amps, and that since there's a negative sign, this needs to be supplying. That's what the passive sign convention tells us in the first place, that if it's a negative power, it has to be being supplied. And traditionally, that means that if you've got the positive current flow, as we have depicted here, that means that this must be the negative terminal, or otherwise you don't get the right number, obviously, right? We know that P equals V times I, so we know that negative 20 equals some voltage times the 5 amps of current, and so V must equal negative 4. And if we just say, all right, well, here's the plus sign, and we keep it that way, we say, all right, well, then there happens to be 4 volts across that with the polarity as indicated, with A at the lower potential and B at the higher potential. Nothing particularly surprising there, I don't think. Another quick example, we have, again, something that's generating something going on. A random device hooked up here. Two terminals A and B, we know that this is the negative terminal and that this is the positive terminal. We know that there are 40 watts, and because it's a positive power, we know that it's absorbing the power. And we're trying to define a current flowing around this way. And that's kind of funny, because we know that there's a positive power here, so when we start thinking about the math for this circuit, we're going to say power equals voltage times current. We know that there's 40 watts. That part's easy. But the voltage, and we happen to know that it's 5 volts across here. So we've got a current that's entering the negative terminal. We end up with a positive power. So obviously that means that if we've got negative 5 volts times the current, easy division, we've got negative 8 equals I. So that makes sense. We say, well, we've got negative 8 amps of current flowing around that way, but all you have to do is start thinking, well, that actually means that the current is flowing the other direction. It is flowing counterclockwise in this circuit. It's entering the positive node, the positive terminal, so we get a positive power. That element can be absorbing the power from the circuit that's being generated by this cloudy part of the circuit. So nothing particularly odd there, but it's just some small applications of the passive sign convention. Again, just to summarize, we know that we have the 20 volts across, or 20 watts being supplied by this device, and we knew that we had 5 amps of current flowing in there. Do the math, and as long as you obey the passive sign convention, we got a negative voltage, so that means that A was going to be the lower potential, B is the higher potential. Same kind of thing here. We know that we were absorbing 40 watts. We knew that we have 5 volts across it. Run that through our P equals VI. We get negative 8, and that makes sense that we actually have a negative current as the way that we defined it. So nothing too weird there. It is kind of a couple of very contrived examples, to be honest. But next thing back on the PowerPoint slides, we've got independent and dependent sources, and we'll see them. Primarily, what we'll see are going to be independent sources, and those are things like batteries. They're things like wall plugs, that kind of stuff. And they are usually depicted on on a circuit diagram using some sort of an independent voltage source. Is almost always just a big circle with some sort of labeled polarity for the voltages and some sort of magnitude of voltage that it happens to create. And that's what an independent voltage source looks like. The symbols that I'm using are going to be consistent with what's in the textbook, and those are not always consistent with the IEEE standards or what you might see in other circuit diagrams. Occasionally, especially for DC sources, you will see something that looks like this, indicating that that's some sort of battery that also tells you the polarity, because the larger line tells you the higher potential, and they'll mark the magnitude of the voltage being created. And so that is, that's what you may see in some other places. Occasionally for AC sources, you will see a curvy line with the positive and negative stuff on it. For the most part, this is the one that we're gonna stick with. Even when we get into AC sources, we're going to stick with that, and we'll just change the notation of what the magnitude is of the the voltage that's being created and include the phase information. Independent current sources, we just draw a little circle with an arrow, and that indicates the direction that the current is flowing, and we give it some sort of magnitude for the current that's flowing around. I don't remember seeing too many other symbols in the past other than this for a current source. So occasionally you'll see something with this little tilde squiggly line for an AC source, but that one's pretty consistent. So those are independent sources. Dependent sources they're interesting, and they become something that we'll focus on a little bit more later. And what you'll end up seeing for those is there will be, instead of a circle, it'll be a little diamond. You'll have a plus and a minus telling you what the polarity of the voltage is, and then the magnitude of the voltage will be defined in terms of something else, so maybe 5 times Vx. And Vx needs to be some sort of quantity that's defined somewhere else in the circuit, and we'll take a look at a couple of examples of that real quick. So that's what a dependent current or voltage source looks like. A dependent current source is the diamond with a little arrow in it, and again it would be something called like 5 times Vx. It's important to note, though, that these can be both a dependent and dependent current and voltage sources. They don't need to be defined in terms of a voltage or a current or something. Well, they do. The quantity here should be either some sort of voltage or current, but you can have voltage-controlled voltage sources, voltage-controlled. CTLD is going to be controlled. Voltage-controlled voltage sources. We can have current-controlled voltage sources. And what that means is that you're going to see something like that the voltage from that dependent source will be something like, call it V dep equals 5 times Ix. Now, that current will be in terms of amps, and Ix would be 6 amps, 32 amps, whatever. And the voltage is going to be, it's still going to be a voltage, but you're just going to say 5 times that 6 amps gives us 30 volts that are going to be supplied by the source. So it's kind of weird when you have a voltage or current-controlled voltage source. You can also have a current-controlled current source, and that makes a lot of sense. It's just the dependent current equals 5 times some current somewhere else, and a voltage-controlled current source. And again, that's going to be something like, or we're going to see this dependent current, and it's going to be given in terms of some sort of voltage Vx. Again, that voltage will be a voltage, but the current would be some sort of amperage. So we'll see all of those. The place that you will primarily see this, we're going to use them almost as toys and something that will just kind of add a layer of complexity to the circuits. But the key thing where this is going to become very useful is starting to analyze transistors in electronics. They're traditionally modeled as dependent sources. So, yes. So, back to the PowerPoint for a couple of, let's see, actually, no, we don't want to go back to the PowerPoint. So a couple of really trivial examples. I mean, these should be tremendously trivial. But we've got some sort of voltage. We know that this Vx equals 2 volts, and we have some dependent source somewhere else in the circuit. It's got something happening. This is going to be a voltage-controlled voltage source, and this is 20 Vx, and this is our total V dependent. So what does V dependent actually equal? 2 times 20. That's obviously that's incredibly trivial, but that's the kind of thing that you're going to see. There's some sort of voltage somewhere else in the circuit that we will, normally what we're going to end up having to do is solve for it, or write an equation that will give us the solution for that voltage, and then we'll plug that in to get an idea of what the voltage that's actually being created is. Very straightforward, very trivial. You could do the same thing with a current source, but I'm not going to because I don't think that you guys are idiots. So, moving on. Next, the last thing that we can do with this is if we combine the concepts of power with the principle of the conservation of energy, we can use this as a kind of parlor trick way of solving for unknown quantities in a circuit. Now, what's kind of silly about this is that in like 10 minutes, we will talk about a remarkably easier way to solve this problem than the way that we're going to do it here. But for the purposes of examples, it's not bad. All right, so we've got a circuit. It's got some devices in them. We're just going to call them 1, 2, and 3. And it's got an independent current source, an independent voltage source, and a dependent voltage source. And now we need to start filling in the rest of the quantities. We know that across this current source we happen to have 6 volts, and it is producing, and we're going to call it Ix, it's producing 2 amps worth of current. So, and so that, this should match up. We're generating 2 amps of current, and we're in this same branch of the circuit. We're generating, we see that there's 2 amps worth of current. We've got this device 1, whatever it happens to be, 6 volts across it, and we want, what we're going to try to find out here, the unknown quantity is what we're going to call I0, I sub 0. We know that over in this branch there are 9 amps of current flowing, and across device 2 there is 12 volts. This dependent current or dependent voltage source is controlled by the parameter Ix up here. And so you can even right now, you say, well, I know what Ix is. It's been measured as 16 amps. Or it's been measured as 2 amps, and so this is going to be a 16 volt source. This independent source here creates 4 volts, and there happens to be 8 amps of current flowing through it. And across device 3, we've measured that there's 10 volts, and there happens to be 3 amps of current. Now, one of the things that we'll take a look at very quickly here is that Kirchhoff's current law says that all of the currents coming into a node, the sum of the currents coming into a node has to equal the sum of the currents leaving the node. And so if we look at this spot right here, we see that there are 3 amps coming in, there are 2 amps leaving on that branch, and 2 amps and something leaving on that branch. 3 minus 2 is 1. And so we know that I0 better equal 1 amp. Because, I mean, there are much easier ways, and that's the easiest way to analyze this particular circuit. But we can also use conservation of energy in saying that all of the power that's generated by the circuit needs to be consumed by the circuit. And so we can start determining the powers of all of the devices in this circuit and find the missing quantity. So, one that we know, the power across that 2 amp source, we've got current entering the negative node. So we've got the 6 volts that are across it, and we've got the negative 2 amps that are flowing through it. And by calling it negative 2 amps, we're just making sure that we're obeying the passive sign convention and that the current is entering the positive node of the terminal, right? That's the point of making this negative 2 amps. Our positive sign convention said that we need to bring the current in, if the current is flowing into the positive node of the voltage, of the voltages as it's labeled, then we can just multiply the signs and the magnitudes together and get a power. So this is currently got the current flowing into the negative node. If we just change the sign, we change the direction of the current, then it's flowing into the positive node. So we have 6 times negative 2. So we've got negative 12 watts that are being created there. And so the current source is supplying 12 watts to the circuit, and that makes sense. It should be doing something like that. The power in device 1 is the one that we don't really know quite yet. It's got to be, we know that there's 6 volts across it, and all we know is that there's that current I0 that's flowing through it, and so the power is going to be 6 times I0 when whatever I0 is solved to be, and we'll have to figure that out later. Across device 2, we've got 12 volts across it, but again, the 9 amps of current are flowing into the negative terminal. And so again, if we need to change the direction of that current in our minds by changing the sign of the current to make sure that it's flowing into the positive node and so that we're obeying the passive sign convention. And obviously, I'm sticking the A there, obviously you could also change the polarity of the voltage and say, well, now I declare that this is the positive terminal, that's the negative terminal, that's the positive terminal, that's the negative terminal. You could do that, and that would be fine. But and it's going to work out the same. One of the two things, either the voltage or the current, is going to have a negative sign. You're going to end up with a negative power. So 12 times 9, that's negative 108 watts. Power across device 3, again, we have to change something because the current is flowing into the negative terminal, negative labeled terminal of the voltage. So let's change, just for kicks, to show you that it doesn't matter, let's change the polarity of the voltage and say there's negative 10 volts and there's 3 amps rolling in. That still is negative 30 watts. Doesn't matter. The power across the 4 volt source is going to be, we know that there's 4 volts across it. Again, we have the current rolling into the negative terminal of the label voltage, so we need to change one of them. In this case, I don't think it makes a lot of sense to try to switch the polarity of the voltage because this is voltage source, and we know that this is the higher potential. So let's leave that as positive 4 volts and negative 8 amps. So that's negative 32 watts. Even though my notes say negative 24 watts. I can multiply. And then the power in the dependent source is going to be 8 times the voltage across it, which is defined as 8 times Ix. And I left off a current here. There's a current of 11 amps that are flowing down into that. That's flowing down into the positive terminal of the voltage, so we're okay there. So we've got 11 amps flowing around there. 8 times Ix we already figured out is 16 volts times the 11 amps, and that equals 176 watts being absorbed. So what do we do with all of this? We've calculated all of these powers. Again, what the principle of the conservation of energy says is that if we sum all of these up, it better add up to 0 because energy cannot be created or destroyed. So I'm going to scan this up just a little bit. All right, so there are all of our equations, and we sum these up. And it should all add up to 0. So we've got the negative 12 watts from the 2 amp source. We've got the positive 6 IO from device 1. We've got negative 108 from device 2. We've got negative 30 from device 3. We've got negative 32 from the 4 volt source. And we've got positive 176 from the dependent source. Add all of those up. And what you should get is that, and I should just do this to make sure that I get it right and not just trust the notes. So we have negative 12 minus 108 minus 30 minus 32 plus 176. So we get negative 6 plus 6IO equals 0. Put the negative 6 on the other side. 6IO equals 6. IO equals 1 amp. And that's all there is to that one. And we got the same answer that we expected to get that was up here that Kirchhoff's current law tells us that we should get. So those are actually, it's kind of tricky to create these kinds of questions and make sure that you do it right. Not last summer, but the spring before that, so I guess it was in spring 2007, I created one of these problems and I forgot to beta check it before I put it on the exam, and was actually unsolvable. The equations did not work out in any way, shape, or form, and that kind of made people a little grumpy on the exam, so now I make sure that I check all the questions. But so you can use that. I would encourage you not to, because it's going to be obviously it took us a fairly long time to make that happen, and it's probably not one of the most intelligent ways that you can go about solving it, especially when I could tell you the answer in a much, much quicker form. So, but you can do it. Summing up all the stuff from chapter 1. Standard prefixes, you should get to know at least some of these. The ones that will be most important to us now are going to be the milliamps, or the milli prefix of 10 to the negative 3, the kilo prefix of 10 to the third, and those will keep us busy for the first little while. Eventually we are going to see we're going to see some micros show up for the microfarads, measuring the capacitance. And we will see a certain amount of mega when we start talking about some of the larger power systems. But it would be worth your time to make sure those are good in your mind. I always get the little ones screwed up, the difference between pico and nano and micro and so on. Standard units, the key ones that we're going to pay attention to and are going to be most important to us are going to be the amp and the volts and the watts, at least to start with. And just as a reminder, whenever you have an SI unit that is a last name, the unit abbreviation is an uppercase character, but when you start writing out that unit, you use a lowercase as the first letter of the word. Relationship between current and charge. Current is the movement of charge over time, and it's a derivative relationship there, and so there's an integral relationship between charge and current going back the other way. Power is the movements of energy over time, or work done over time, and we're normally going to think about that as just being voltage times current. And there are more fancy ways that you can calculate it, but for the most part, P equals VI will suffice for our needs. Passive sign convention, it's important to keep this one straight. If you write out things such that the current flows into the positive node of the voltage, as you have them labeled, and you have all of the associated magnitudes and signs of those quantities there, when you do the multiplication, it will tell you what the magnitude is of the power that's either being absorbed or supplied, and it will tell you whether it's being absorbed or supplied. A negative power is one that is being supplied to the circuit. A positive power is power that's being absorbed by that element of the circuit. The passive sign convention, being very clear on that, will keep you doing well in the rest of the class. And then conservation of energy, all circuits obey it. Basically, all of the power that's created by a circuit needs to be absorbed by the circuit. Or else we would, if you can figure out a way to circumvent this, you'd probably not have to work a day in the rest of your life. So let's move on to chapter 2. I'm not going to spend a lot of time with the homework in chapter 1. Most of it is very trivial and doesn't really give us much. So we're going to just kind of move on to chapter 2, which is starting to look at resistive circuits, and we will add in some more, and I'll post a homework assignment later today for you to start working on looking at these resistive circuits. Key things that we will look at here, as electrical engineers, you should know Ohm's law already to some extent, but V equals IR, and we will dig into that a little bit more. We will look at Kirchhoff's current law, which I already alluded to, which is the sum of the currents entering a node is going to be the sum of the currents exiting the node. Kirchhoff's voltage law basically says that around a closed loop, all of the voltages sum to 0. We'll look at those and applications of those. And then we'll start looking at some actual honest-to-goodness circuits, some single-loop circuits where we can use especially Kirchhoff's voltage law to solve for some unknown quantities. Look at single-node pair circuits, again, using Kirchhoff's current law. And then look at how resistors can be combined to make a simpler looking circuit, and then add in some dependent sources to all of these things. And that's going to be the normal progression through all of these topics. Will be, let's look at them with independent sources first, and then look at them with dependent sources, because dependent sources always complicate things. So current doesn't always flow nicely. I don't know of any ideal conductors. We have some pretty good conductors, but they still have some amount of resistance to the flow of current. All of the mechanical engineering friends that I had in my undergraduate days thought about it as water flowing through pipes, and sometimes there's rust on the inside of the pipes that impedes the flow of the water. And that's the same kind of idea. And the degree to which the flow of current is inhibited is called resistance. The first person that quantified this relationship and measured it is a guy named Georg Ohm, and he got the unit named after him as well. Rather than using an O, it uses the capital omega for indicating a resistance. And yeah, in AC current, technically, there's an impedance is the entire quantity, which is a complex quantity that contains both the resistance and the, shoot, I can't remember the other part of there's two components. The real component is the resistance, and the reactive component is, we'll get to it. But the entire concept is called the impedance. The current voltage relationship here is very straightforward. It says that the voltage across the resistor is directly proportional to the current flowing towards it, flowing through it, or V equals I times R. If you multiply the resistance times the current, that will give you the voltage, and obviously then you can mess around with that. I think that that Ohm's original formulation of this law said that, I think it was I equals V over R. So that if you know the voltage and you divide it by the resistance, that tells you how much current is flowing through it. I think that was originally how he formulated it, and we tend to think about it as V equals IR. So you've got those two really easy but very fundamental equations: P equals VI, V equals IR. And so an ohm is technically defined as a volt per amp, if you rearrange the terms in Ohm's law. So one thing, we'll look at it in a second. So then we can do some simple arithmetic, some simple algebra. If we remember P equals VI, and we know that V equals IR, then we can make two substitutions and see that power equals resistance times the current squared. If we stick in, so that one would be sticking in I times R for V. So if you square the current, multiply it by the resistance, that tells you the power that's being absorbed by the resistor. And V squared over R also gives you the power. Now the important thing, and it's just tremendously key, is those squared terms. And remember, the passive sign convention tells us that if you define it with the current flowing into the positive labeled terminal of your voltage, then multiply the currents and the voltage together, and that should give you your power. And if your power is positive, then you have something that's absorbing power. Is it possible ever to get a negative power with a resistor? And it's not. When you have a squared term in there, it's not possible. I mean, unless you happen to have an imaginary amount of current flowing through there with, I or J being the amount of the current flowing through, that's the only way you can square a number and get a negative number. Otherwise, whenever you square it, no matter which way that you've defined the voltage and current, you're going to end up getting a positive number. Or in other words, resistors always absorb power in a circuit. Power is nonlinear. That's also important. As you start increasing the voltage, increasing the current, then the amount of power that's being dissipated is going to increase, in a quadratic form and not a linear form. But the relationship between voltage and current is still linear. The opposite of resistance is conductance. We don't really use conductance a whole ton, or at least I don't. There are certain textbook authors that find conductance to be a remarkably useful concept, and I have never been one of the people that really likes conductance. All of the laws and stuff that pertain to resistance also apply to conductance, because conductance is just defined as the inverse of resistance, or 1 over the resistance gives you the conductance. The unit for measuring conductance is Siemens, named after Ernst Werner von Siemens. He did a ton of EE stuff. If you're ever bored, you can go look up Siemens on Wikipedia or something and waste a good 5 minutes reading about him. He did all kinds of stuff. Not the least of which, you may have some Siemens electronic stuff around in your house. Siemens is a big name in that stuff, and it was originally founded by Ernst. The unit abbreviation these days is an S, indicating that it was Siemens that it's named after. And I think I looked this up and I forget what it is, but the conductance is almost always assigned to a variable G. Resistance is almost always assigned to a variable R. And obviously R makes sense for resistance. Conductance, YG, I forget what the answer is. There is a meaningful thing. I think it's in honor of some other guy. But just as a historical aside, when my brother-in-law went through engineering college in it should have been like the early 90s, late 80s, conductance was measured in mhos, which is obviously the backwards of ohm. And the symbol was an upside down omega. And some electronics and like audio files still talk about mhos instead of Siemens. Just FYI, I suppose. So we can define Ohm's law and the current voltage relationship in terms of conductance instead then. And so if conductance is 1 over R, then you just stick that in, you get I equals G times the voltage. I don't find that to be at all memorable, and I also really don't find it to be particularly useful. But I want you to be aware of it. Power you can also define as I squared over G, and power it can be voltage squared times G if it's worth it to you. I will always work with resistance. I don't find conductance to be at all helpful. So that's my personal take on it. A couple of things. So to this point, I've ignored telling you about the goodness of the circuit elements and what it looks like to have a resistance in a circuit. So if we look at the document camera, we have, whenever we see a resistance, what we will draw is a little squiggle. And it's important that it's a very kind of triangular squiggle, because we will run into other kinds of squiggles later. And then indicate that there is some amount of resistance across this, say 12 ohms. And occasionally I will get lazy about dropping the units, but it's kind of assumed that that's what's going on here. This particular circuit element picture symbol is really only used in the United States. I think everywhere else the IEEE is standardized on just a little skinny rectangular box and saying, okay, that's 12 ohms. So that's what you may see in a lot of other documents and circuit diagrams. And I think this is everywhere else. I don't know why we continue to use this one. I still like it better personally, but I suppose that's because that's how I learned these circuits in the first place. So there are a couple of important resistances that are worth kind of noting as well. We have a short circuit, where resistance equals 0. And then we have an open circuit where the resistance is ostensibly infinite. And so there are some important quantities that are important outcomes of having a zero resistance or having an infinite resistance. So let's start with, so this was the short circuit, and this is the open circuit. So let's take a look real quickly for the open, because that's what I started writing. We have, so the current flowing through something is given as the voltage divided by the resistance. Well, if we know that the resistance is infinite, well, what does that make the current? Is it L'Hopital's rule or whatever? Or is it just general stuff that says that's 0? Whenever you have 0 in the or infinity in the denominator, that drives the answer to 0. Whatever. Whoever said it, that's the practical result of it. And so what that means is that when you have an open circuit, 0 current flows. That's the practical takeaway, and that's the math behind why it works that way. We define that as being an infinite resistance. For a short circuit, we say, well, the voltage across something is equal to the current, I of t, times the resistance. So we know that the current, the resistance is 0. So we have some sort of current, whatever that is, and the resistance is 0. So that means, well, there's 0 voltage across in a short circuit. Those are the takeaway messages. Short circuit, no voltage. Current can still flow, provided there's some sort of driver, but there's no voltage across it. In an open circuit, there's no current flowing between those 2 points because of the infinite resistance. So, all right, what's next? All right, doing a little bit of work with Ohm's law and finding some interesting results out of it. I need to get out my notes here. Okay. So these are all pretty trivial, but they kind of help illustrate the point. So here's a circuit. It's got an independent voltage source in it, and it has a resistor in it. And the resistor has a measured resistance, or we looked at the little bands on the resistor and found that it should be about 2 kilo ohms worth of resistance. And we have a 12-volt source. So the unknown quantity in this particular circuit is the I. What is the current that's rolling around through the circuit? And we just use V equals IR. V equals I times R. I is the unknown quantity, so I equals V over R. The voltage is 12 volts. The resistance is 2 kilo ohms. And so this is how I will normally write out these equations, just so you're aware. I will kind of drop out the units on a fairly regular basis to keep the work looking somewhat clean, and drop off but not dropping off the kilo ohms, because that part's important, because that's going to hugely affect the magnitude of our answer. And so just as a little bit of a rule of thumb, if you have something that's in the ones or tens of volts and you divide it by something that's in the kilo ohm range, what you're going to end up with is something in the milliamp range. And obviously 12 divided by 2 is 6. So 6 milliamps happens to be flowing around in that circuit. If we wanted to, we could figure out what the power was that's being absorbed by this circuit as well, or by the resistor. And we can do it lots of different ways. We happen at this point to know that there's a current of 6 milliamps running through it, so why not use I squared R? So that's right, I squared R. I always get them screwed up. V squared over R and I squared times R. So P equals I squared times R, which would be 6 milliamps squared times 2 kiloohms. Now this one would probably be worth punching into the calculator, make sure I do it right. So 6e negative 3 squared times 2000 gives us 0.072 watts. And you'll get the same answer no matter how you calculate it. You want to do it V times I, all right, well there's no place else for this voltage to be consumed, or if there's 12 volts across here, there has to be 12 volts across here, and we'll look at that a little bit later. But there's 12 volts across it, or let's look at it this way. We know that there's going to be V times I power generated by this source, and that must be absorbed by this source, or else we have, or by the resistor, or else we have a circuit that's not obeying the conservation of energy. So V times I, 12 times 6 is that same 0.72, or 0.072. Another one, real simple. So we've got a voltage source. We have a resistance, and we know that it's a 10 kilo ohm resistor, and we happen to know that the power being consumed by that resistor is 3.6 milliwatts. We don't know the current, we don't know the voltage of the source, but we have enough information to figure out what's going on. And since we use I squared R up here, let's use V squared over R here. So we know that power equals V squared over R. That's going to be V squared over 10K. The power we know is 3.6 milliwatts, so the 3.6 milliwatts times the 10 kilo ohms is going to give us the square of the voltage. And just make sure we do this right. So 3.6 e negative 3 times 10,000 gives us 36. Yeah. So the square of the voltage is 36 volts. 6 volts equals V sub S. And then you can also find out what the current is if we know that, so V equals IR, and we know what the voltage is, we know what the resistance is, we just need to know the current. That's V over R. So V we found out was 6, the resistance is 10K, and so the current is going to be, let's try to divide instead of multiply. I guess that would be 0.06 milliamps, or 0.0006 amps, whichever way you want to look at it. I guess it should just be 0.6 milliamps, right? I think that's right. It's the biggest decimal point you've ever seen. So anyways, you can keep doing that, and there's a few more examples on my notes, but I think that it's getting kind of sinking in. You can use voltage, currents, and power to solve for anything else, and you can use any one of the equations that happens to float your boat. You just need to use the appropriate things that exist for you. In this case, we knew the voltage, we knew the resistance, so we could just use V equals IR. At that point we had everything. We had the voltage, the current, and the resistance, and so we could use any of the equations to solve for the power. In this case, all we had was the resistance and the power, so we used V squared over R. We could have used I squared R. Didn't really matter. Any of those options are available to you. So use the one that makes sense for you. Gotta get rid of this stuff. All right, so what's next? Okay, a little bit more talking while I get my the rest of my notes together. So as you've noticed, I kind of have a little bit of a thing for history, and so I tried to put in some historical notes for these things. Gustav Kirchhoff was a German physicist, lived in the middle part of the 1800s, and again, he was a German physicist. He married his math professor's daughter, and that kind of caught me for some reason, and I think it's because I do have a daughter, and I don't want any of you anywhere near her. But what is amazing about Kirchhoff as much as anything is that all of these two laws that like really fundamentally define electric circuits were both developed when he was a student. So he was sitting on that side of the classroom, and he came up with this really bright idea about the current law and the voltage law. A couple of definitions to get us started on what these things are about. A node is just a connection between two circuit elements. A loop is a closed path in which no node is encountered more than once. And a branch is a circuit containing one element and the node at either end. So those are three definitions that we need to make sure that are really well understood as we get into the definitions of what makes Kirchhoff's current law and Kirchhoff's voltage law. So node is a connection between two circuit elements. A loop is a closed path in which no node is encountered more than once. And a branch is just a chunk of the circuit where containing one circuit element, and that is one resistor, one voltage source, one independent source, whatever, and the nodes at either end of that. So just in terms of the pictures of these things, look at the dot camera real quick. A node is just one of these little dots in a particular circuit, and so that's a node. And you can start drawing the rest of the circuit around it. Maybe there's a resistor, maybe there's an independent source over here. And what we'll normally do, and we won't always do this, but in between anything that you will need, any two elements, you will need a node, and that's kind of unspoken. So actually, what's important here is that those two nodes, as I've drawn them, these are the same node because there's nothing connected between them. This, you could say there's a node here, but that's also the same node as these other two. It's all the same node because there's nothing connecting them. But if we start saying, well, here's an independent current source, and here's a voltage or a resistor, and here's another resistor, and here's a resistor, and here's a resistor, and here's a dependent source, whatever. Now we can start pointing out a lot more nodes because there's a lot more nodes in the circuit. There's a node here, there's a node here, there's a node here, there's a node here, there's a node here. And those are all of the unique nodes. You could say, well, there's a node here, but that's the same as this node. You could say there's a node here. Again, it's the same as this node along the bottom. So, and you can number them, you can name them, whatever. This is where the double subscript notation that I mentioned yesterday comes in very handy. So if we have, if we just letter them, this particular, those would be resistor RAB, this one would be resistor BC, and so on and so forth. And then the voltage across here would be voltage VAB. Again, whether you think that's important, that's the kind of thing that you want to do, go for it. But I won't tend to do that a ton. A loop. There are 3 loops in this little example circuit that I've drawn here. There is a loop here. We go around this first side. and that's a loop because we encounter all of the nodes just once. It doesn't have to encompass everything in the circuit. There's a loop that goes around this one. Obviously, it only encounters nodes E, C, and D, and the two elements. There's a loop around the outside. No, that's a loop. What is not a loop is to try to catch everything. So you can say, well, let's go around like this. We'll go up and go A and B, C, E, D, because we can't get back without duplicating one of those nodes. So there are 3 loops in this circuit. And then again, a branch, there are lots and lots of branches in this circuit. This is a branch. And it's kind of an oddly shaped and fairly large branch because it is the circuit element and the nodes at both ends. Here is another branch of the circuit. Contains the nodes A and B and the resistor in between them, so on and so forth. Those are nodes, branches, and loops. So, on the slide, very important, Kirchhoff's current law. The algebraic sum of all of the currents entering a node equals 0. So if we take into account all of the current that is rolling into a node, it better equal all of well, there's 2 ways of looking at it. You can say that just in general, all of the currents entering a node has to be 0. But that means that we need to define the difference between current that's rolling into the node and what's rolling out and giving it a different algebraic sign so that this holds. The easier way to think about it, I think, is to say the sum of the currents entering the node has to equal the sum of the currents exiting the node. That's just, I think, the simpler way of looking at it. And that's what we looked at on that example way back at the beginning of when we did the ridiculous power thing. I looked at those branches and I said, well, there's 3 amps rolling up this way, there's 2 amps rolling up that way. Kirchhoff's current law says that the only other way there's one other branch for things to go to, and it better be 1 amp. And that's, again, it's kind of a restatement of the principle of conservation of energy. Everything that goes in has to come out. So that's Kirchhoff's current law, and that goes around. It's talking about any node and going into any node, and so we'll look at some examples of that. Definitions and pictures. Okay, these are fairly academic-y kinds of examples where we don't actually solve for anything, so I'm going to skip them. And let's look at something more interesting. Okay. So, let's see, let's pick a good one. Here we have kind of an interesting, or actually it's an entirely uninteresting looking circuit because there's nothing in it. I don't know how these currents are flowing technically, but whatever. So we've got this window pane circuit. We have a current I1. We have a current, we don't know what that one is. We have a current flowing down through this one at 60 milliamps. We have a current flowing down this one at 20 milliamps. We have an unknown current I5 going that way. We have an unknown current I4 flowing that way. We have an unknown current I6 flowing that way. We have 40 milliamps flowing that way and 30 milliamps flowing that way. Now, one of the things that we will do, and this is, and I should have been more explicit about this, is that for purposes of making the algebra work, and so that Kirchhoff's current law holds in some sort of meaningful form, currents flowing into a node are given a negative sign or a negative magnitude. And current flowing out of a node is given a positive magnitude. I guess it doesn't make sense. It's given a positive sign if it's rolling out, and it's given a negative sign if it's coming into the node. So let's say we number our nodes. We've got 5 nodes in this circuit. 1, 2, 3, 4, 5. And so we can write KCL equations at each one of those nodes, bearing in mind this convention that I didn't just invent it, but so let's write a KCL at node 1. At node 1, we have a current over here, I1, that's coming in. So it's coming in. We're going to call it negative I1. We've got 60 milliamps that are leaving. It's leaving, so we'll give it a positive sign. And then we've got 20 milliamps, again, that are leaving. And KCL, what it says is that the sum of all of those currents entering the node equals 0. And so obviously then it's pretty trivial to solve for I1. I1, put it on the other side. I1 equals 80 milliamps. And this is exactly what was going on in that first one. We had these 3 branches. We had 3 lamps going in. We had 3 amps going in, 1 branch. We had 2 amps going out, 1 branch. Obviously, 1 amp had to be going out the other branch. That's just how it works. Let's look at equation 2. Now, this one's maybe a little bit more interesting. Let's start. It doesn't matter the order of the terms. So let's start on the top and say, all right, we've got I1. It's leaving. So that one's going to have a positive sign on it. We've got I4 that's coming in. So that one's going to have a negative sign on it. We've got I6 that's leaving. So that one's going to have the positive sign. KCL says that equals 0. That's got, well, it's got technically 3 unknowns. We already solved for I1, so not a big deal. We'll come back and look at that one later. At node 3, now we've got 4 currents to deal with. We've got 60 milliamps coming in, so negative 60 milliamps. We've got I4 that's leaving. It's leaving, so it gets a positive sign. I5 is defined as coming in, so it gets a negative sign. And 40 milliamps leaving, so it gets the positive sign. KCL says that equals 0. Fourth equation that we need to write for node 4. Over here, we've got 20 milliamps coming in, so it's a negative 20 milliamps. We've got I5 leaving, that's plus I5, and we've got 30 milliamps defined as coming in, so that's going to be a negative 30 milliamps. Again, KCL says that equals 0. Last equation, and then we can solve and have all of the unknowns taken care of. We've got node 5, we've got I6 coming in, so negative I6. We've got 40 milliamps coming in, minus 40 milliamps. And we've got 30 milliamps leaving, so that's plus 30 milliamps equals 0. So obviously this means that if we do this right, I6 goes on the other side. I6 equals a negative 10 milliamps. Quick solving, we combine the negative 20, negative 30, put that on the other side, we get I5 equals 50 milliamps. So we're down to not having a ton of unknowns. We've got I1 and I6 now, so I1 was 80 milliamps. And I4 we still don't know. I6 is negative 10 milliamps. And we put I4 on the other side, so I4 equals 70 milliamps. And I think that's all the unknown currents. I1, 4, 5, and 6. So I1, 4, 5, and 6. KCL, the sum of the currents entering a node equals 0. And as long as you keep track that the current flowing into the node is always going to be assigned a negative sign, current flowing out of the node gets a positive sign, you'll make sure that you get the order correct and the algebraic signs correct. In a very similar way, and we can write up some simple equations that look at the same thing, Kirchhoff's voltage law says that the algebraic sum of all of the voltages around any loop is 0. and there's the formal loop. You can look at all of the all of the voltages from J up until N. Sum them up, they should equal 0. And there should be an equal 0 on that formula that's not there. And it's the same basic idea as before. So let's look at a couple of KVL examples real quick. Here is an arbitrary circuit. We've got a voltage source in it. We've got a resistor, another voltage source. We've got a resistor, and down here we've got another resistor and another voltage source. So we've got nodes. We're going to label them A, B, C, D, E, and F. And so let's call this R1, R2, R3. And so if we wanted to, we could find out what the value is of VR1, or what is the voltage from A to B. And this is not one that we can solve. We don't have quite enough information, and there's a couple more things I need to draw into the circuit so that we can understand what's going on anyways. Because we don't have the polarities for any of the voltages of the resistors. Traditionally, we just kind of try to make it work out so that it kind of works in a clockwise fashion normally. And again, just like we discussed yesterday, if these are wrong, you just get a negative number for the answer when you try to do the solution, and it doesn't make your assigned polarities necessarily incorrect, and it doesn't make the answers that you've gotten incorrect, just as long as you're consistent about using those. So let's say that's 30 volts. Let's call this a 5-volt source and a 15-volt source. And so Kirchhoff's voltage law says the sum of all of these loops, or the sum of the voltages around this loop, equals 0. So if we wanted to find VAB, or the voltage across that resistor, we just need to write a KVL equation around the entire loop and then solve for VAB. So let's start at VAB for simplicity's sake, and that's VR1, because we ran into the plus sign first. Then we hit this voltage source, we run into the negative sign first, so that's going to be minus 5. We come around here, we run into the positive sign first, so that's going to be plus VR2, whatever that voltage is. We run around here, we hit again the negative sign on this voltage source, so it's going to be minus 15. We hit the positive sign on this, and it's going to be so plus VR3. And then we hit the negative sign on this voltage as well, so it'll be minus 30. KVL says that the sum around that entire loop equals 0. So VAB is going to be the same as VR1. So all you have to do is throw all that stuff on the other side, and you can find out what the voltage is across that. So negative 5, negative 15 would be negative 20, negative 30. So VR1 equals VAB equals, I guess that would be 50 minus VR2 minus VR3. And that's as simplified as this particular equation can get in this case. Let's see if we... Okay, let's do one more quick example. Because this is a pretty reasonable example. All right, try to draw this out quickly, include all the information. All right, 24 volt source, 16 volts across, R1, 12 volts across that source. This is R2. It has 4 volts across it. This is R3. It has 6 volts across it. We have 10 volts across R4. And again, label these A, B, C, D, E, F. Okay, so what is the voltage between nodes A and E? And what you can do is find out what the voltage is between any 2 points by using what you know about KVL to make that happen. So as we just take the voltages as we run into them, we get positive 16, minus 12, positive 4, and positive 6. Sum those up, so that's 16, positive 4, positive 8, positive 14. That's the potential between these 2 points in the circuit. And that should work out for us that if we were to go around the rest of the way, it should still equal 0. So if we're here and we know that between here and here there's 14 volts, we get an increase of 10, so that brings us up to positive 24. Then we run into the negative 24, 0 around the entire loop. Everything's good. One last quick one before we let you go. VEC. So we start here, we run into the 10 volts here, negative 24 volts from the source. We got 16 volts at R1, and we got negative 12 at this source. Sum that up, so that's negative 14, positive 2, negative 10. So that's KVL. There are much more interesting things that we can do with KCL and KVL, and that's what we'll look at tomorrow. So have a good one. Don't forget Quiz 0, and we'll talk with you on Wednesday.